Okay, we're going to start, or today we're going to tackle the topic of line integration. We're going to do this a few times. It's not just a single module at this point. This is one of the newer things that's in the course. I think other things we've talked about in the course so far have been review of some kind, or at least to the extent they're new, they've haven't been too difficult. But line integration, I don't want to say it's difficult. It's just maybe new. So we're going to talk about line integration. We're going to talk about line integration in the planes. We're just going to look at a 2D contour or curve to begin with, and things will get more complicated as we build up from there. Okay. When we're doing line integration, one of the tricky things, it's true of all vector calculus to some extent, what we're going to do is we're going to have, in space, some line. Okay. And we're going to generally call that line a curve C. And the fact that we call it a curve doesn't mean it's curvy. This is also a curve, right? This is a curve, right? That's just a piecewise continuous curve. But just because we call it a curve doesn't mean it has to be curvy, right? So this is a path. And there's going to be some function that defines that path. And then there's going to be a function that we have defined over this 2D space. Okay? And we want to know what the sum, or the integral, of this function over 2D space is as we walk along this path. Okay? So it's a different idea. The contour itself is the path in 2D space, and if you kind of think of it like we're walking along that path, and at every point in the path we ask ourselves, well, what's the function at this point in the path? You grab it and you add it. Then you take a new step down the path. What's the function? Grab it and add it. And the fact that you can take a curvy line through is going to affect the value of the function, or the integral. So there are two functions at play. There's a function that's defined over R2, or over any region containing the curve C. And then there's going to be some function or description of the curve itself. And we're going to have to keep these two things straight. We're going to do an example. We're doing a series of ways. This is kind of a long module, actually, this first one. And it's really just part one of several for line integration. There are different kinds of curves, and the note module describes these, right? We've already talked about parameterization of curves, and the reason we talked about that is because we need it now. So we could have curves that are smooth. So this would be a smooth curve from A to B. We could have piecewise smooth curves. We could have closed curves, which are going to be very important, where we come around and finish back at the point we started. We might go around them more than once. That's simple closed. Or we could have crazy things, okay, which are not simple but closed. There's going to be different ways to deal with each of these things. These first three are quite simple. A lot of the time we don't concern ourselves, or we exclude simple closed, or I'll show you other ways to handle simple closed. You actually treat them as two different curves, each one being simple. But we'll get to that when it matters. Now, the other thing is, when we first introduce line integration, we think of maybe three flavors of line integral. To be honest, this is going to be less important when we go on, because when we go on, we're actually going to combine them. But right now, there are three different ways you could conduct or execute line integral, and when we do an example, we'll do all three, and they're different. So same curve, same function over the curve, just three different questions we're asking, or three different differentials that we're summing. Sometimes we're summing based on the extent we move in X. Sometimes we're summing based on the extent we move in Y. Sometimes we're summing based on the extent that we move along the curve. That last one probably is what sounds most normal. Like, well, we're walking along the curve, we should talk about how much the function varies as I walk along the curve, which is really integrating along the arc length. It's mildly more complicated than the other two. When we do the first example, we'll do all three. Okay? But the idea is, this is kind of the language we're going to use. We draw an integral with a C under it. It doesn't always, but in the context of this course, that's going to mean line integral. There are times where we're going to draw something like this, which is going to be a line integral that's closed. So an integral over something like this, where we integrate back to our starting point. Okay? They're not always like that. So in general, we're going to have an integral, we say sub c, just to be general about it for a minute. And then let's say we have some function x and y. This is the function that's defined over the space. And the first case, I'm going to say I want to know how the function is varying as I move in x. Okay? So I'm going to move along this c, which is to be determined. I'm going to sum this function based on increments in x. You could also calculate a line integral of the same function over the same curve, but concern yourself with how much the function varies as you step in y. Then finally, you could say I'm going to go along the same curve, same function, but now I'm going to ask, that's d sub s, I'm going to ask how the function varies as I step along the curve itself. So the first one, if this is x and this is y, as I change, I'll consider the change in value of g divided or sort of multiplied by the step in x. But if I'm integrating this guy, I care about the change in g multiplied by the step in y. So this is dx, this is dy. And the last one is I'm going to concern myself with the change in g and multiply that by the total change along the arc, which is ds. You can sort of see that ds is some sort of combination of x and y. Okay? And we'll see that when we do this first. The examples help us through this a lot. Okay? Okay, so we're going to start, and this is, I'm just going to say this, then we're going to do an example. It's going to take a little while to go through the example. It's kind of full-on integration akin to what you did second semester last year. You're going to remember some things. Okay, so we're going to start with the parameterized curve in the plane. Okay, parameterized curve in R2. Okay, so we're going to stay in the XY plane. Later we can do this in 3D, but it's just not, we don't need that complexity right this minute. Okay, so we're going to assume that C is parameterized. And we already looked at how you parameterized a path, a line in 2 space. So we're going to say x is equal to some f of t, and y is some g of t, right? And then we're going to let t vary from some a to b. If it was a closed curve, a would equal b. Okay. So when we do this then, this integral, when we do this, is going to become an integral from t, that t goes from a to b, and we're going to take g of f of t, to replace all the x's in g with f of t, all the y's with g of t, and then dx is going to be f prime t dt, right? Because df dt, well, basically we would say that dx, yeah, that equals f prime, right? And yeah, that's the derivative with respect to x. So dx dt is equal to really df dt, because x is equal to f. So that means dx would be df dt times dt, so we say f, the derivative of f with respect to t at dt. Okay, took me a second there, but that's how that would look. Okay. Now notice how everything is known there, right? I'm going to know the function of f, I'm going to know the function of g, so I'm going to know the function of g as x and y, so I can put f of t and g of t in there, and then I'm going to replace this dx by, I'm going to calculate the derivative of f with respect to t, put that in here. And then we just have an integral over t. This integral, if I'm doing the y one, dy, similarly, t goes from a to b, g is evaluated at f of t, g of t, and then I replace this with g prime of t dt, right? Because this is dy. Finally, if we're integrating along the arc length, then we're going to have something a little bit more complicated. F of t, g of t, and now we have the square root of f prime at t squared plus g prime of t squared square root dt. And this gets into the case where we said we're going along the curve and I care about the change in ds. It's really the change in dx and the change in dy. So dx, dy, ds. So ds squared equals dx squared plus dy squared. Therefore, ds is the square root of dx squared plus dy squared. And that's kind of what we're writing here. Well, it's not kind of, that is what we're writing there. Okay? Okay, this is formally, that's in the notes, that's in the textbook. Now let's do an example. And just because it's, as usual with these things, I think it's easiest to see an example. We're gonna pick a certain g of x and y, we're gonna give a certain curve, and then we're gonna calculate each of these kinds of integrals. Okay? And they are more or less difficult. Sometimes they're easy, sometimes they're not. So let's do that. And this example is actually example right out of the textbooks. You can, furthermore, if you don't like the way I do it or you need to see it a different way, you can look at how the book goes through it. So here's the example. So we're going to let g of x and y be x, y squared. This is the function. It's defined everywhere in R2. So for any x, y, you have this function over this 2D space. Okay. And then we're going to let g of x and y, and then we're going to let c be defined as the quarter circle of radius 4 from an angle of phi equals 0 to phi equals pi over 2. So this is what C looks like. Okay. This is x, this is y, this is 4, this is 4, okay? And we're going to go from here to here, okay? And when we write it like this, it's a quarter circle. So x is going to equal 4 cos t, y will be 4 sine t. So this is us parameterizing the curve because we recognize this is a circle. So as t goes from, and t will go from 0 to pi over 2. Okay? T equals 0, x equals 4, y equals 0, and t is pi over 2, y is 4, x is 0. And in between, the sum of those squares, these guys squared up equal 4 squared. So this is a circle radius 4. Okay? So this is C from here to here. This is G. I want to integrate this as we move along that curve. Okay? We're going to do it 3 ways. So first way, we're going to calculate C, G, X, Y, dx. Okay? So this means I want C, X, Y squared dx. And what we're going to do first is we stick the definitions of x and y as parameterized with t into the function. Okay? So x equals 4 cos t. That means that we're going to need dx. So dx by dt will be minus 4 sine t. So dx equals minus 4 sine t dt. Okay, and we have y equals sine t. So those were given. And we calculate, remember we said we replace dx with the derivative of x with respect to t and dt. So this integral then, I1 I'm going to call it, equals, okay, so t goes from 0 to pi over 2. X, 4 cos t, y squared, 4 sine t all squared. Okay, dx, minus 4 sine t dt. Now just simplify that a bit, but now we have this integral in t, and now we're just doing first year. Okay, so this is x, this is y squared, this is dx. Okay. So this thing equals 4, 16, 16, so 256. Okay, it's actually minus 256 because the negative comes there. Pi over 2, 0. And now we have sine cubed t. And I have cos t dt. Okay, and that's the integral. We could have that been given that integral last year or any time in calculus. So this is a substitution. We'll let u equals sine t, and then du will be cos t dt. So we'll let, here we go. Okay, so this will be du, this will be, so this is the same. So if we just think for a second as an aside, this means we have the integral of, u cubed du, right, which is u to the 4 over 4, okay? And so this guy then, this integral, I1, be minus 256, and then we'll have 1/4, then we'll have u to the 4, which is sine, so sine to the 4t, be evaluated at pi over 2 and 0. Right? Okay, so this thing becomes minus 64, and this thing becomes sine to the 4 pi over 2 minus sine to the 4 at 0, right? And this is 0, and this is 1, so this whole thing becomes minus 64. Okay, so that's this integral. This integral for this function, for this curve, in this direction, to this extent, is minus 64. Okay? That's the procedure we go. Okay. So, okay, it is the only tricky thing about it, once we parameterize the curve and we're told what that is, right? And this is something you need to be able to see, okay? We have a circle that you can parameterize circles as cosines and sines. Okay, and this should make sense, especially once I show that this is what this is. Then it's kind of just a recipe, right? You make substitutions. You let x equal its parameterized value, y its value. dx becomes the time derivative of the x component, dt. And then you're just doing an integral like you know how to do. Okay. So now, let's see, how do I do it? This next part's a little longer. Well, okay. I'm gonna leave this side over here. Okay, just because that's where our problem is said, or stated, so I can go back to that. Okay. Let's calculate the other integral. So, now I want this one. I want the line integral, okay, of x y squared dy. So it's the same idea, right? So this is going to equal pi over 2, 0, let's limit it at x, and I have x for cos t, just like last time, y squared for sine t squared, just like last time. Now I need the derivative of y. Okay, so the derivative of sine, right, will be 4 cos t dt, right? Because the dy dt is 4 cos t. So dy is 4 cos t dt. So this is dy, this is y squared, this is x. Okay? So this thing, again, 256 times. So this is, I'm just going to try to get a little compressed here. This is 256 times equal 0 to pi over 2, and we have sine squared cos squared. T cos squared t dt. Now sometimes there's sneaky ways to remember these things. This one's actually kind of harder to remember, at least the way I did it when I break this thing apart. And the book does it really fast. So remember, right, that sine A plus minus B is sine A cos cos B plus minus, you do cos A sine B, right? And cos A plus minus B is, this is where you get the square. Cos A cos B minus plus sine A sine B. Okay? These are the double angle formulas. Not double angle formulas, the angle addition formulas. Okay? And so this guy means sine of 2A, right? So if A equals B, then this thing equals 2 sine A cos B, oops, jeez, cos A, right? And this guy means that cos of 2A is cos squared A minus sine squared A. Now those ones we can recast as, for example, cos squared is 1 minus sine squared A minus sine squared A. So this becomes 1 minus 2 sine squared A. Okay, and that means that sine squared A equals 1/2 cos, 1 minus cos 2A. Okay, so sine over here, so if I have sine squared cos squared, so I know that sine t cos t squared, okay, which is what I have in the integrand, that is 1/4 sine squared 2t. Okay. And I know what sine squared of something is, so this is 1/4 times 1/2 of 1 minus cos, this is twice, that should be 4t. Okay. So this would be 1/8, 1 minus cos 4t. Okay. That's what sine squared t cos squared t is. 1/8, 1 minus cos 4t. So we can simplify that, and now we can integrate that thing. Okay. So our integral up here, I2, so our I2, I'll just write I2. So I2 would equal, okay, 256 divided by 8, and then pi over 2, 0. Now I have 1 minus cos 4t dt. Okay, so this thing, now we can do this. This is 32. Okay, and then we have this, so that's just t. Okay, and then we have minus, the antiderivative of cosine is sine, with the chain rule, so this becomes 1/4 sine 4t. That would be the antiderivative of the cos term. 0. All good so far? Okay, good. So this would be 32 pi over 2 minus 1/4 sine. 4 pi over 2 is 2 pi. Right? Sine of 2 pi is 0. Okay, we won't do that. Okay, minus 0 plus 1/4 sine 0. So this thing just becomes 16 pi. Okay, so I know, you're saying, well, I don't know if I'd remember how to do that. Well, we need to start to remember how to do this. These kinds of equations, we had to just bring up some of these muscles we had before, right? When you get to this, this does become just an integration challenge, right? And remembering how to handle these things is something we had to do last year, and we need to pull that up. We'll try when we do these. We're not really trying to trick you on your ability just to do a 1D integral. The important thing here is parameterizing this thing and getting to that integral. The rest of this execution is something that we have to train ourselves to remember. Okay. Notice that this I2, it's not the same. When we integrate this xy squared dy, it's not the same as xy squared dx. They're different things. Okay. Okay. So now, let's do the third case. Okay, that is the integral over the arc length. Okay, so now it's not dy or dx, it is both in a sense. It's the square root of the sum of squares of those two things. Okay, so now we're going to calculate I3, where we're going to say, okay, I want g x y ds. Okay, so this is integral of 0 to pi over 2. And we have the same thing we've had before, 4 cos t, 4 sine t squared. Okay, and then now we have, well, let's leave this for a second. Okay, so ds, right, is the square root of x prime of t squared plus y prime of t squared, dt. Okay, so this is actually going to turn out easier than we would think. So this is square root. X prime was minus 4 sine t squared, plus, and this is 4 cos t squared, dt. Okay, so this becomes square root 16 times square root sine squared t plus cos squared t dt. This is 1, right? Sine squared plus cos squared equals 1. So this whole thing becomes 4 dt. It doesn't have to work out this easy, right? But it does in this case. When you're doing circle stuff, it kind of will turn out this way, right? But we didn't have to remember that. So this is what ds will be. So really, way up top here now, I just take this thing, that's what goes here. So this becomes 4 dt. Okay? Well, you just do this systematically. Okay, so our I3 then just becomes, so we have here, we have 4, 4, 4, we still have 256, and we have pi over 2, 0, then we have, what we got? Yeah, sine squared t cos t dt. We did this before. U equals sine t, do u equals cos t dt. Okay. So this thing will turn into the antiderivative of u squared du, right? And so that will be 1 over 3u cubed. So this guy then will be 256 times 1/3 sine cubed t, okay, at pi over 2 and 0. Okay, and so this thing becomes 256 by 3, and then we have sine cubed at pi over 2 minus sine cubed at 0. That's 0. This is 1. So this thing becomes 256 over 3. Okay. So we've got 3 different line integrals along the same function, same contour, just different forms. Okay. There is one aside here that we can do. So that's execution of all that. Let's just check. Well, that's not. Okay, sure, let's do it. Let's do it. Just for a minute, just about the arc length for a second. Okay, So we had here, in the middle of that calculation, we said, okay, ds is 4 dt, okay? So just for a second, remember, we want to remember what the arc length is. It's the sum of steps along the path. If I just integrated ds along this curve, what should I get? I should get the circumference of a quarter of a circle. That's what the sum of these little steps would be. I'm not integrating g ds, I'm just integrating ds. So if I had like this, see, and I just do this, we expect this thing to be 1/4 the circumference of a circle of radius 4. So let's just check for a second that that's what you would actually get. Okay, well, we still go pi over 2 to 0, but now I have 4 dt. Okay, we've just parameterized. It's like we're integrating g equals 1. And so this is 4 times t pi over 2 and 0. So this becomes 4 pi over 2 minus 0, which is 2 pi, right? The circumference of a circle radius 4 would be 8 pi. So this thing is 1/4. So that makes sense. That's what should be happening here. Okay? It's just, the reason we're just saying that is we want to not lose track of what the physical, if you like, definition of ds is, right? It's path, it's called arc length. So when we have a line, you know, we're doing some integral, and I'm going from here to here, and I just look at dx, I just integrated dx from this point, I know it's the length of this line. And the dy would be the vertical extent of the line, which is 0. When we have a curve, it's the length of that curve. That's what ds is. Right? So a little integral step along that. So we can sort of check, I'm not sure if we use it to check, but make sense of that. And there are lots of times where we'll end up with something, or sometimes we'll end up with integral of just ds. And I want to quickly sort of check that. Okay? So that's our first set of examples of doing a line integral. We might call it a contour integral later on, but that's loose. That's using words that are ahead of us. We'll just call it a line integral for now. And so they're sort of easy and they're sort of hard. They're only difficult in 2 ways. First is getting it set up. So knowing what the function we're integrating is, that's sort of easy. It's this part here, it's parametrizing it, that it takes a little bit of a step. Once we have it and we say, oh, I see x equals 4 cos t, y equals 4 sine t, t from 0 to pi over 2, that's this curve, then it's formulaic. It's not that the formulas are easy, right? The second integral was a little bit difficult. Maybe you guys have a smarter way to do it than I do. That's very possible. I'm not great at those things. But then it just becomes executing the integral. Okay, we're going to move on next to cases where we don't parameterize the curve with respect to t. We're going to parameterize the curve and make this a function of x or a function of y, which in some ways is easier, may or may not be. But the basic processes be the same. Okay, that was a long module, and now the modules may take up almost a whole class each time. We'll see as we go. Okay.